In this section, we're going to introduce a new map called the exterior derivative. This is going to give us a way to see how the gradient, the curl, and the divergence all arise naturally from this particular map. So what this map is going to do is this is going to be a map that takes J forms to J plus 1 forms. So let's start with 0 form. So we wanted to find a map that's going to take a 0 form, or in this case a 0 form field, to a 1 form field. So we're going to just go ahead and define this. So let's let omega be a 0 form field, i.e. omega is just some function. And we're sticking with just working with R3 here. So I'm going to define my map dw. This is going to be the partial of f with respect to x dx plus the partial of f with respect to y dy plus the partial of f with respect to z dz, which we'll also write in shorter notation with the subscripts. Okay, so we can see clearly this is a 1 form, so clearly we have dw is a 1 form. We'll often just write w as f, so we often just write this as df instead of d omega. There's no real reason to introduce more notation here. So let's go ahead and see what this actually does. So let's consider a point. We'd like to relate this to stuff we already know. Consider a point P that's x0, y0, z0, and a vector v, which we'll write as v1, v2, v3. So we have our 1 form field. So the first thing we would do is we would plug in a point of this to get an actual 1 form. So if we do that, this is f sub x at x0, y0, z0 dx plus f sub y x0, y0, z0 dy plus f sub z x0, y0, z0 dz. So now this is just a 1 form, and so that means we can plug in our vector v to this. So if I plug in v here, this is going to be f sub x, and I'm just going to put the p in here rather than writing the x0, y0, z0 to save a little effort, dx of v plus f sub y of p dy of v plus f sub z of p dz of v. And we know dx just projects onto the x component, dy onto the y component, and so on. So this is f sub x of p v1 plus f sub y of p v2 plus f sub z of p v3. So this should look pretty familiar to us. In particular, we have, remember, the gradient of f, x, y, z, is just f sub x, x, y, z, I, plus f sub y, x, y, z, j, plus f sub z of x, y, z, k. So in particular, if I plug in p, the gradient of f at p is just f sub x at pi plus f sub y of p j plus f sub z of p k. All right, so this is just familiar stuff from when we define the gradient. But in particular, if we look up here now at our derivative, our exterior derivative, just note that dfp of v is exactly the gradient of f at p dotted with my vector v. So this is a way to kind of define, see how the gradient actually comes out naturally from this exterior derivative. It's just coming out as what we dot here with. So if we have that v happens to be a unit vector, then we know this dot product here gives us the directional derivative. So then we'd also have, this is actually recovering the directional derivative of f in the direction of v at the point P. So that's pretty nice. That gives us a way from this map here It's just that we defined up here for our one form to go from a zero form field to a one form field, we recover the gradient out of that. So our next step is going to be, well, what would we want to do if we start with a one form? So what about D going from a one form field to a two form field? And our definition above was somewhat justified because we saw we got the gradient out of that. However we define this, we'd also like to get something interesting from that as well, or something we're familiar with. So let's start with a one form field. So we can write this as, say, omega is equal to f dx plus g dy plus h dz. That's a typical one form field. Now how I'm going to define this, so we define this exterior derivative. Well, if I take d omega, what I'm going to do with this is for the first term, I'm going to take that exterior derivative I already defined for the f, and then wedge that with dx, and then do the same thing for the other terms as well. So that's how we're going to define this, and we can see maybe it's not as obvious that this is a two form yet, but let's go ahead and simplify some of these. So let's simplify. So I know that df, we define that above, that's fx dx plus fy dy plus fz dz from above. Now if I want to wedge that with dx, well, I'm going to have f sub x dx wedge dx plus f sub y dy wedge dx plus f of z dz wedge dx. And now we know dx wedged with dx is 0, so this first term goes away. And then we want to change the sign of the second term, so we get one of our basis forms here. So we get dx wedge dy, and then we got plus f sub z dz wedge dx. So that's what we get from the first one. And now we can go ahead and do the other ones as well. So if I do dg wedge dy, I'm going to just write out the answer for this. You can go ahead and pause the video and check and make sure you see where this is coming from. So this is going to be gx dx wedge dy minus gz dy wedge dz, and then dh wedge dz is equal to minus hx dz wedge dx plus hy dx wedge dy, or dy wedge dz. So let me change the order here to put it in the correct order. So this is h of y dy wedge dz minus h of x dz wedge dx. So those are all just simple calculations, but remember these are just the three pieces on the right hand side here of dw. So let's go ahead and write down, gather all those pieces together. Then what I get from this is I get h of y minus g of z dy wedge dz plus f of z minus hx dz wedge dx plus g of x minus f of y dx wedge dy. Okay, so this might or might not look familiar. Depends how often you've been working with stuff like this recently. But we're going to go ahead and see kind of where this comes from. So let's make a new definition here. So let's suppose we have a vector field. And let's write this vector field as f, let's say pi plus qj plus, say, rk. So we can easily associate a one form to this. How do we do that? Well, we just use the coefficient. So we use this subscript f here on our omega to indicate that it's coming from f. And this is just going to be p dx plus q dy plus r dz. And don't get confused here with the f there. That's not a point. It's just indicating that this one form comes from this vector field. And this is sometimes referred to as the work one form. We'll see why. And when we go back to integration, you can probably kind of figure it out from what we've already done with one forms. And we can also associate a two form. So in this case, same notation. This is just going to be p, and we're going to do dy wedge dz plus q dz wedge dx plus r dx wedge dy. And now, if I look at the derivative of the one form above, so take the derivative of this, maybe we put a little 1 here to indicate a 1 form and a 2 here to indicate the 2 form. So d omega f1, well, if we work this out, we just did this above, and so this is going to be r sub y minus q sub z dy wedge dz plus p of z minus r of x dx wedge dz plus q x minus py dx wedge dy. And this might look familiar now because we're using p, q's, and r's. So if we were to take the curl of our vector field f, this would give me exactly these coefficients. So what we see here then is that the derivative of this one form is actually giving me the two form that comes from the curl of f. Okay, so this is a way that we recover the curl, and this gives us an idea that, okay, what we defined above seems to work pretty well because we're getting something back that we're interested in. So this is familiar. So we've seen so far, that grad and curl both arise naturally when using the exterior derivative. Okay, so our definitions before, when we first introduced these things, might have seemed a little artificial, especially the curl, and upcoming is the divergence. But in this case, they come out very naturally from this definition of the exterior derivative. So maybe let's take a second to do an example. Make sure we see how this works. So let's let f of x, y, z just be x squared y plus e to the z. So then df is going to be the partial derivative of this with respect to x, so 2xy dx, plus partial derivative with respect to y is just x squared dy. Partial derivative with respect to z is ez dz. So this is just my one form field here. Now what would happen here if we take the derivative of this one form? So d of df. Well, that means I want to take the derivative of 2xy and wedge it with dx plus the derivative of x squared wedged with dy plus the derivative of e to the z wedged with dz. Now, for this first term, let's maybe write this separately. Remember, this is going to be the derivative of this function with respect to x, so 2y dx, plus the derivative with respect to y, which is going to be 2x dy. So I have here, I'm going to have 2y dx wedge 2x dy all wedge with dx. And then if we do the same thing for this one, I'm going to get a plus, and I'm going to get a 2x dx wedge with dy. And then this last term here, the derivative with respect to this is just going to be ez dz, and then wedge dz. So we know if we're wedging two of the same things together, we're going to get rid of them. So I'm going to have a 2y dx wedge dx plus 2x dy wedge dx plus 2x dx wedge dy plus e to the z dz wedge dz. Now, when we have the same ones, these go away. So this is gone and this is gone. And then I can change the order to write this as 2x, negative 2x dx wedge dy plus 2x dx wedge dz. And this just gives me 0. And this is going to be true in general. If we take the exterior derivative 2 times in a row, we're always going to get 0. And so as an exercise, just verify that this makes sense to you, that df is equal to 0 is equivalent to this fact that we had from vector calculus, that if we take the curl of the gradient, this gives me 0. Well, it should be the 0 vector. So check that you see why those two things are equivalent. So naturally, next we want to look at our exterior derivative that's going to take a 2-form field to a 3-form field. So how are we going to define this? Well, let's start with the 2-form omega. So let's say this is f dy wedge dz plus g dz wedge dx plus h dx wedge dy. And we're going to do pretty much the same thing we just did. So I'm going to define d omega to be df wedge dy wedge dz plus dg wedge dz wedge dx plus dh wedge dx wedge dy. And now this is a bit of a mess, but we're going to be able to simplify this a lot. So this is fx dx wedge fy dy plus fz dz, and then this is wedge dy wedge dz. And similarly, I'm going to get gx dx plus gy dy plus gz dz wedge dz wedge dx plus hx dx plus hy dy plus hz dz wedge dz. And now notice, for when I'm doing these out, I'm going to have a lot of cancellation here. It looks messy, but we have a lot of cancellation. So this dx is going to stay there because there's no other dx. But this dy, when we wedge, that's going to hit that dy, and that's going to go to 0. And this dz is going to hit this dz, and that's going to go to 0. So the only thing that's left in the first term is fx dx wedge dy wedge dz. And now for the second term, we see this dx is going to hit this dx and go to 0, and this dz is going to hit this dz and go to 0. So the only thing we're going to have left is gy dy wedge dz wedge dx. And finally, for the last one, we forgot. We made a mistake on this last one. This should be wedge dx wedge dy. And so they're going to get rid of this dx and this dy, and I'm going to have hz dz wedge dx wedge dy. Okay, now we want to simplify this as much as we can. So this first one, that's in good form. We'll leave that one how it is, because that is the volume form. The second one is not quite the volume form, so I need to switch the order. So I need to move this dx here, which is going to introduce a -1, and then I'll introduce a -1 there as well. So let's do this in 2 steps, though. So I'm going to get a negative out front, and I'm going to have dy wedge dx wedge dz. So I've switched the x and y, or x and z spots. And I need to do the same thing for the next one. So I'm going to say negative HC, and this time I'm going to move the dz, so I'm going to have a dx wedge dz wedge dy, and then do the same thing. So again, leave the first one alone because it's already in the correct volume form. And now I'm going to switch the dx and wedge dy, and that's going to give me another negative sign, so that cancels out, and I have dx wedge dy wedge dz. And similarly, this is going to switch the dz and the dy, and I get dx wedge dy wedge dz. And so this is fx plus gy plus hz dx wedge dy wedge dz. Which is pretty nice here because notice this looks exactly like the divergence. So if we take, say, F to be a vector field, and then I associate my 2 form with this, so this would be F dy wedge dz plus g dz wedge dx plus h dx wedge dy. Then if I take the derivative of that, that gives me exactly fx plus gy plus hz dx wedge dy wedge dz, which we could write as the divergence of f dx wedge dy wedge dz. So this is a way to see how the divergence falls out of our definition for the exterior derivative. So this is going to make, using this language, will make all of our big theorems, Green's theorem, Stokes' theorems, divergence theorem, they're all going to look really nice, and fundamental theorem of line integrals as well. We'll be able to write them in a really simple way that's going to be really nice. So this leads to nicer forms of the main theorems. We'll see that later. And so in those big theorems, I always told you, like, when we were looking at those, to think of like the curl as like a derivative of the vector field. And now we see what's actually going on is the curl actually does come from the derivative. It comes from the exterior derivative. So it is a derivative. So all of these things that looked totally different, the gradient, the curl, and the divergence, those look nothing alike when we learned them. But we said think of all of them as a derivative. Now we see they're all coming from this exterior derivative. So they're all the same thing, really, just in different dimensions. So now there are no higher forms. We've seen that, but that makes sense because if we had, so suppose we wanted to do a 4 form, or suppose we wanted to try to do D to go from a 3 form field to a 4 form field. Well, we already know there are no 4 form fields, but we can actually see why now as well, because if I had omega was f dx wedge dy wedge dz, and I tried to define that the same way. I tried to say d omega then is df wedge dx wedge dy wedge dz. Well, we can see this is going to be 0 because this is fx dx plus fy dy plus fz dz. And then I'm wedging that with dx wedge dy wedge dz. And we can see this dx is going to cancel with that. The dy is going to cancel with that. And the dz is going to cancel with that. So this is going to be just 0. It's just another way to see there's no 4 form fields that come out of this. Okay. So as we saw before, we said that we could take d of df, and that would be 0, was equivalent to this thing that we had before, that if we took the curl of the gradient, we got a 0 vector. Well, you can do the same thing here. If I take d of d omega, where this is a one form, and then so when I take the df, this becomes a 2 form. So this is going to be 0 as well, and you can check that this is equivalent to the divergence of the curl is equal to 0. So maybe check these as an exercise. And so you just check that you see why they're equivalent. You can, of course, check this just like we checked before. We just write out what it is and see that it has to be 0. So one more concept I want to talk about what makes these forms really nice and these exterior derivatives really nice is the change of variables. So when we did the change of variables formula, it seemed we ended up with the Jacobian, which seemed a little weird. We did it from geometry, but the formula was a little bit funky to kind of remember. So let's think about this. So let's suppose we want to do two variables. And three variables is going to follow the exact same way, and I'll leave that as an exercise. So think of we're like writing things in x, y, and we want to change to r theta. So that's kind of our example to keep in mind here, is changing from rectangular to polar coordinates. So what happens with two form fields? Okay, well, let's think of writing x as x of uv for some new variables u and v, and y is equal to y of u of v. So think of this as like x is equal to r cosine theta, y is equal to r sine theta. That's kind of our prototypical example. Now, if I take the derivative of this, we can just use chain rule to see, well, the derivative of x here, this is going to be the partial of x with respect to u, so maybe let me write it out with partials the first time, du plus the partial of x with respect to v dv. Remember, thinking of x as a function here, so it looks a little funny because we're used to writing f's here, but in this case, think of x as f from before. So x is our zero form field. And so we can, of course, write this as x sub u du plus x sub v dv. And similarly for dy, our one form that comes out of this, this is going to be y sub u du plus y sub v dv. So those are our one forms we get out of this. Now, when we're doing change of variables, remember what we were doing was looking for areas, so we needed to see how our area element changed. So our area form in xy coordinates is dx wedge dy. Remember, that was what was giving us our little incremental area and gave us when we plugged in two vectors, it gave us the area of the parallelogram spanned by those vectors, right? So when we plugged in v and w, the dx wedge dy of vw was the area of this. So this was our area form. So I want to see, well, what happens to this in our new coordinates? So when we change to y, or to u and v, well, let's replace the dx. So I have xu du plus xv dv wedge yu du plus yv dv. And so if we do this, distribute this across, I'm going to have xu yu du wedge du plus xu yv du wedge dv. Remember, the order is important here. xv yu dv wedge du plus xv yv dv wedge dv. Now, of course, the du wedge du and the dv dv go away. So this gives me xu yv du wedge dv plus xv yu dv wedge du. And so changing the order, I get xu yv minus xv yu du wedge dv. And so this looks pretty nice because this thing here is exactly our Jacobian. I'm going to write this maybe as xy uv. So let's close with the quick example that we said above. Just recovering this again, with x being r cosine theta, y being r sine theta. If we do that, then x sub, in this case r, is going to be cosine theta, y sub r is going to be sine theta, x sub theta is minus r sine theta, and y sub theta is r cosine theta. So that means dx wedge dy is, well, we're going to put these in out front, so we're going to have xr y theta minus x theta yr dr wedge d theta. And so this is cosine theta r cosine theta minus r sine theta dr wedge d theta, which is r cosine squared theta plus r sine squared theta dr wedge d theta, which when we simplify this, the cosine squared plus sine squared becomes 1, so I just get r dr wedge d theta. So that's where that scaling factor of the r comes from. We showed where it came from when we were looking at polar coordinates by looking at the geometry and drawing pictures. But if we think of these just in terms of the one forms and two forms, it falls out quite naturally just from changing the variables like this. So in the next section, we're going to actually go back and we're going to look at integrals. We've already saw line integrals with one forms. We're going to now look at surface integrals with two forms and volume integrals with three forms. So that will be next time.